So it's always a pleasure to introduce the speaker of the colloquium, but today is really a special pleasure because the speaker today is Sakura Pascarelli, who is a very well-known person here in Grenoble, a dear colleague and friend. And let me nevertheless briefly summarize her career. She studied physics in Roma at University La Sapienza, and where she got her laurea. And after spending some time in Frascati, she came to Grenoble to work on the Gilda Sergi beamline and did a PhD at Université Joseph Fourier, which she completed in 1997. She was then hired at ESRF as a scientist and became involved in developing instruments for local spectroscopies via X-ray absorption. In particular, she worked on developing XFELs and magnetic dichroism spectroscopies. And scientific activity has been focused on extreme conditions, in particular extreme pressures, temperatures, and high magnetic field. She has been in charge of several absorption spectroscopy beamlines, ID24 and BM23. And then she became head of the group in charge of electronic structure and magnetism, and then of the group in charge of matter at extremes. And a little more than a year ago, in 2019, she was appointed scientific director at the European XFEL in Hamburg, and where she's in charge of the scientific program for the hard X-ray instruments. And the title of her presentation today will be the European XFEL, Start of User Operation and First Results. Sakura, we're eager to listen to your presentation. Thank you.
Thank you, Patrick. Let me share my screen with you. There you go. Can you see my screen? Yeah, okay, good. So first of all, I would like to thank Patrick for this invitation. It's an honor for me to be speaking at this very, famous ESRF ILL colloquium series. I'm also sort of, very happy to be back home. Unfortunately, I can't see you, but I have been missing Grenoble and the ESRF. So I left a year and 4 months ago, and I have to say that the separation with France has been quite brutal, especially due to Corona. But I have been following what's going on at ESRF, and I'm very, happy to see the start of this wonderful machine. And we're all, here very excited to see first results from ESRF EBS. And I would like to take the opportunity to congratulate all the ESRF staff for this great achievement. So today I'll talk to you about the European XFEL that started operation a few years ago, and go through a few first results, and then I'll give you my view of the challenges that we have ahead. So the European XFEL started in 2009. That's when the construction started. It is funded by 12 countries, but mainly Germany and Russia. So the European XFEL is actually in charge of constructing and running the X-ray laser, whereas DAISY constructed and operates the accelerator. So we have part of the staff at XFEL and part of the staff at DAISY, and they take care of the accelerator. Operation of the first instrument started in July 2017, and here are a few numbers to show you that this is a big, facility. It's a very expensive facility. It was expensive to construct, and it is expensive to run. And the goal is to perform 200 experiments per year. And at the moment, we're pretty far from this goal. So a few words for those of you who are not familiar with XFEL radiation. This radiation is actually very different from synchrotron radiation. First of all, as you can see here on the right, the pulse duration is much shorter. It's of the order of tens of femtoseconds, whereas at synchrotrons, the pulse length is typically of the order of 100 picoseconds. Also, the peak intensity is orders of magnitude higher. But most importantly, what is different is the distribution of photons as a function of energy. As you can see here, it's very spiky, and it's very, let's say, it has very strong fluctuations pulse by pulse. And also the distribution of photons in space is also very spiky. And you can compare it to what you have. This was calculations from the previous machine, ESRF. You see a very nice smooth undulator harmonic as a function of energy, and a nice smooth, distribution of photons in space. So this is very different. And the reason it is so different is because these photons are generated through a stochastic process. So you have a linear accelerator, exactly like you have at ESRF, but this is a very long accelerator, much longer, and the electron beam is accelerated to higher energies. So here we are talking about 17 GeV. And these electrons, they are injected in bunches. So you have an electron bunch that then enters an undulator. So these undulators are just like the ones we have at the ESRF, except for they're much longer. So the undulators here are of the order of hundreds of meters. So what happens is that this little bunch comes in and starts wiggling, and at every wiggle, it generates photons, and this happens at the resonant wavelength. So at this resonant wavelength, you start having electron density fluctuations. And these fluctuations, they just amplify as the bunch goes through the undulator. So they amplify, and you start having the formation of micro bunches within the bunch. Okay, and within the micro bunch, at the end of the undulator, in the so-called saturation conditions, you have all electrons within one microbunch that are aligned, and they emit coherently. And this is the reason why you have these very, very sharp spikes that you can see in space and also in time. Now, so as I said, a characteristic of this radiation is the very short pulse length. So now we have femtosecond pulses, and we can start doing, ultra fast science, just as we can do, and we have done for many, many decades, using optical lasers, except for now we have wavelengths that are of the order of the angstrom. So with these hard X-rays, we can start really doing ultra-fast science with chemical selectivity. We can pick the atoms we want to go and look at. We have bulk sensitivity. And if we can reduce the pulse a little bit more, because at the moment I'm talking about tens of femtoseconds, but if we could go down to the femtosecond or so, we could even follow not only the atomic motion, the phonons, but also charge motion from one atom to the other. Another thing is that these machines have actually modified the way we do structural determination with X-rays. And 20 years ago, there were simulations and theoretical simulations showing that you could actually use an extremely intense photon beam concentrated in a very short pulse to obtain structural information from a system before destroying it. So you could obtain all the structural information you need before radiation damage actually sets in. And this has been verified. And so today we can take snapshots of molecules, and we can actually, excite the molecule with an optical laser, modify its structure, and then using pump and probe methods, we can follow how the structure, evolves. And this is what we call making movies, molecular movies. This is all possible now. So just to put the European XFEL into context, I'm showing you here a map which shows the main, let's say, XFEL facilities. So around the world, in orange are the soft X-ray facilities, and in dark blue, the hard X-ray facilities. So I will focus on the hard X-ray facilities. The first one was LCLS here in Stanford, in California. This XFEL started operating in 2009. And in the following decade, there's been 4 additional facilities: Sakla in Japan, PALFEL in Korea, and the European XFEL in Germany, and SwissFEL in Switzerland. And you can see that among all the XFELs that are operating today, the European XFEL is the only one that reaches megahertz repetition rate. And the reason it can reach such high repetition rates is because it is powered by a superconducting accelerator, which allows to sort of concentrate much more power in these pulses. Now the LCLS has just been upgraded, and it can also now operate at megahertz repetition rates, except for at the moment only in the soft X-ray regime. And so in the future, this will also be extended to the hard X-ray regime. And there are also other facilities coming up, especially in Asia, that are going to be of the same kind as the European XFEL. So this is a photograph from the top. So Hamburg city is here on the bottom right, and you see here the Daisy campus with the Petra ring. So our injector is here in the campus underground. And you see here this very long linear accelerator, which is underground. This is a photograph of the cavities. So at this point, the electrons have been accelerated to about 17.5 GeV, and then they enter into different tunnels where they produce photons when they interact with the undulators. So these are the photon tunnels. These are the beam lines, which are also very long. And these X-ray photons are then delivered to the instruments, which are in a big experimental hall underneath the office building, which is shown here. So at the end of the accelerator, as I said, these electrons are injected into different tunnels. And you see here, they interact with the photon sources. So we have 3 undulators. Sorry, go back. 2 of them are hard X-ray undulators, SASE-1 and SASE-2, and 1 of them is a soft X-ray undulator. So each of these sources is feeding photons to 2 instruments. So we have a total of 6 instruments at the moment. 2 of them are soft X-rays and 4 are hard X-rays. So I'm going to say a word on the structure of these pulses. So the accelerator works at 10 hertz, and which means that it produces a macro pulse or a bunch train every 100 milliseconds. So in this bunch train, we can fit up to 2,700 pulses at a maximum repetition rate of 4.5 megahertz. We typically work at 2.2 megahertz, but occasionally we have gone all the way up to 4.5. So this means that the smallest time distance interval between 2 pulses in this train is of the order of 200 nanoseconds. Now, each of these trains delivers photon bunches to every instrument. So one train will give bunches to SASE-1, SASE-3, and SASE-2, meaning that these 3 instruments can work actually at the same time. Okay, so as I said, we have now 6 instruments in operation, and I will just very briefly go through them just to present them. So we have here on the left, the 2 SASE-1 instruments. These are hard X-rays. These were the first to become operational in 2017. On the top, we have the SPB-SFX instrument led by Adrian Mancuso. SPB-SFX stands for single particle and biomolecules and serial femtosecond crystallography. So this instrument mainly caters the bio community. Here we have the FXE instrument, which stands for femtosecond X-ray experiments. So here, this is mainly the catalysis, the chemistry community. They look at ultrafast phenomena, mainly in solution. They couple spectroscopy with scattering, for example, both emission and absorption spectroscopy, but they mainly do solution chemistry, also some solid state. Here in the center, we have the 2 soft X-ray instruments, and they became operational at the end of 2018. So here on the top is SCS, spectroscopy and coherent scattering. On this instrument, the main topic is solid state physics. They look at strongly correlated electron systems, a lot of magnetism, and here they are commissioning a big RIX spectrometer. And so they often combine absorption spectroscopy with small angle or wide angle coherent scattering. Here we have the SQS instrument. SQS stands for small quantum systems. So as the name says, they look at atoms, molecules, nanocrystals, nanoparticles. And they also do a lot of nonlinear physics, and they're looking at all these nonlinear phenomena with very, very intense beams. Here on the right, we have the last two instruments, which are the SASE-2 hard X-ray instruments, and they were the last to become operational in 2019. Here on the top, we have the MID instrument. MID stands for Material Imaging and Dynamics. This is the instrument led by Anders Madsen, and I think that many of you remember Anders. He was at the ESRF for many years. So here they use techniques such as a lot of coherent scattering. They do XPCS, X-ray photocorrelation spectroscopy. They are involved with the community of soft matter, some biology, a lot of material science. And finally, here on the bottom, we have the HED instrument, high energy density. So here they use a lot of drivers to, bring matter to high pressures, high temperatures, high magnetic fields. And I will be spending a little bit more time on this instrument at the end of my talk. Okay, so now I have picked a few examples of experiments, results from these instruments. Some of these relate to early experiments, and therefore we have some publications. Others relate to much more recent work, and some of these are even experiments that were carried out virtually during the corona restriction time. And so you will see some Zoom screens of users that I imagine you also have at the ESRF. So this is the first example. Now, one of the, let's say, the dreams of these new XFELs, hard X-ray free electron lasers, was to be able to, use these very high intense pulses to determine the structure of a small molecule, like a small protein, at atomic resolution. Now, this is still a dream in the sense that we're not there yet. But there's been a lot of work done at LCLS, and we're also continuing in this direction to try to get to this goal. And this is the example that I'm going to show you. So just to say a few words on how this works. So the idea here is that you drop single particles into the beam. So they interact with this with these pulses of X-rays, and then you take a single coherent diffraction pattern for every particle. And then you take the totality of these patterns, and using reconstruction algorithms, you reconstruct the three-dimensional structure of your particle. Now, the problem here is that in order for this to work, not only you have to take a large number of patterns, but every pattern has to have a sufficiently low background so that every single image contains some sort of information so that you can, for example, realign the patterns. Now, all these challenges have been addressed at SPB from the start, and there's been this first paper that came out very recently where, it really shows the advantages of having a megahertz repetition rate for this kind of applications. So this was a test sample. It was a small gold nanoparticles of different shapes, different sizes. It was a whole population of with a distribution of different kinds of particles, and they were able to reconstruct this whole population with a very good spatial resolution. And it shows how important it is to have a lot of images, because then you can start doing statistics. So this looks very promising as a future step towards, one day being able to do this imaging of molecules at atomic resolution. This is one of the first images we have. This is taken on the soft X-ray instrument SQS. It's diffraction from a single protein. So this is a 14 nanometer molecule, so it's a big thing. And you see, this is the experimental data. These are the simulations, 2 different simulations using 2 models. And the resolution is not that great in the sense that what we can conclude from this data and from the background is that we can say that, this hole is filled with water. It's not empty, and which is good. But okay, we're not yet at atomic resolution, but this is where we are now on SQS. Okay, this is another kind of experiments. This is work on FXE, femtosecond X-ray experiments. This is a Swiss group that has been working for many years to study these heme proteins, like hemoglobin, myoglobin, cytochrome C. So these heme proteins all have a very similar structure. They're based on a porphyrin ring, and they have an iron in the middle. So people study these because they're very important proteins for our body. They carry small molecules. For example, you know that hemoglobin carries oxygen in our blood and into our muscles. They're also responsible for transmitting signals to the brain. So, you know, people really are interested in knowing, you know, the structure and how these proteins actually work. So hemoglobin has been the most studied one, and it is well known that when the ligand is detached, so when, for example, the oxygen leaves this heme ring, the iron undergoes a low spin to high spin transition, and it pops out of the plane, and the heme goes into this domed, sort of strained, domed shape. So the goal of this experiment was to understand whether this change is something which is generic to all the heme proteins, or whether it's a specific thing for hemoglobin, and also to use the femtosecond resolution to identify, you know, the relationship between the spin change and this structural change. So what the group did is they used an optical laser to detach the small molecule, the ligand. Okay, so the laser gives enough energy for this ligand to be detached, and then they use pump and probe methods to follow the changes in structure and in the electronic structure of the iron to try and identify what I just said. So the experiment was carried out at XFEL and European XFEL. So at XFEL they did femtosecond resolved XANES, and at XFEL they did the emission spectroscopy. This is because we are still not able to do XANES, and hopefully this will change in the coming months. But the conclusions were that, first of all, they find this effect also in cytochrome C. So this is a generic feature of you know, the doming. And the data taken at XFEL was able to demonstrate that, you know, iron undergoes a series of many different spin states, a cascade of spin states, and they could really identify all of them thanks to the femtosecond resolution, and they could relate that to the structural change. This is another example of work on FXC. So this is very recent. It was carried out in August, and it is, as you can see, one of our virtual experiments. So the team was from the US, led by Jim Penner-Hahn, University of Michigan, and they were all connected through Zoom. And these are the staff, the two staff members sitting in the control room. So Jim has been working for a long time on vitamin B12 and different forms of vitamin B12. Vitamin B12 is really important for us. It's an essential nutrient, and it's important because it's involved in it catalyzes many chemical reactions inside our body. And people are interested in understanding you know, the different forms of this vitamin. So it's a molecule which has a cobalt atom in the center, and it has different kinds of ligands. And depending on the kind of ligands, you have different forms which behave differently, and they have also different behavior in the excited state. So they have studied all these different forms in the lab using optical laser spectroscopy, and they do not understand why these different forms behave differently. And so they come here because they want to understand from the atomic point of view, you know, the relationship between the function of these molecules and their structure. So Roseanne was at the user meeting on Wednesday here, and she showed how they are advancing in the interpretation of the data. So this is K-alpha and K-beta on cobalt, and the results look very exciting. And so we look forward to seeing some publications here. Okay, now I move to the soft X-ray instruments. This is work done on SCS. It's a collaboration between a group from MIT and Max Born Institute. These groups have been working on studying magnetic Skermions. So magnetic Skermions are magnetic topological quasiparticles that can reach very, very small diameters. As you can see here, this is an image where the dark dots are, you know, the areas of the sample that are magnetized in one direction. So the spin is pointing in one direction, and the white areas, the spin is pointing in the other direction. Now, why are these things studied? Well, Skermions are now, you know, becoming a very hot topic because of their potential for the development of faster and more efficient data storage devices. So up to now, people were manipulating these Skermions using electric currents. But now more and more, you start using lasers to manipulate them. And they were interested in looking at in following, you know, using femtosecond resolved wide angle and soft and small angle scattering. They were interested in following the transition from a homogeneously magnetized state to this topological phase of Skermions. And what they did was they heated the sample. So you have a multi-layer that is magnetized in certain homogeneous magnetic state. They heat it with a laser and they bring the sample into a phase where you have fluctuating spins. And then this phase cools down and goes down into this topologically stable Skermion phase. So you see the nucleation of these Skermions. And they figured out, they understood that actually the presence of this highly fluctuating, so high temperature, right? Because the laser heats the sample. This highly fluctuating spin phase is really critical to be able to overcome this energy barrier, which makes the topological phase so stable, right? So stable against thermal fluctuations. And this is really important because the stability is something which you really need for these storage devices. Okay, this is work from the other soft X-ray instrument, SQS, and it has also been recently published. It's a very nice method that was developed by this group. So it's SQS team in collaboration with a group from Max Born Institute in Berlin. They developed a method based on photon recoil imaging, which allows to identify very rare processes. So these are nonlinear processes that occur in the interaction between X-rays and atoms. And I'm going to try and explain it in a simple way. So what they're looking at is basic interactions between X-rays and atoms. So they have a collimated atomic beam of neon, okay, that is just propagating, and then they send an X-ray pulse on it. And you can see here, this little segment here, orange segment, is the, you know, the footprint of the X-ray beam on this atomic beam. Now, some of these atoms will interact with X-rays, and the X-ray energy is chosen to be able to induce this electronic transition from the 1s to the 3p state in neon. So X-rays interact with the neons, and some of these undergo this electronic transition. And so you have neon atoms that are in this excited state, and as you know, the atom wants to then de-excite back to the ground state. And we know that typically this can occur either in a radiative way or in a non-radiative way. If you follow the non-radiative process, you emit Auger electrons and you get into an ion. And that's not what they were looking at. They were not interested in this specific process. They wanted to look at the radiative de-excitation, which brings this excited state all the way down to a neutral atom. And they were measuring here behind, they put a position-sensitive detector to measure the position of these neutral ions and seeing where they landed. Now, you see this radiative de-excitation can happen actually in two ways. The normal one is that you spontaneously emit a photon. So this is the very well-known fluorescence emission. And this photon goes all over the place. It's just emitted isotropically, which means that this neutral atom that you get as a final state and that you measure here has received a recoil energy that puts him all over the place, right? It gets a little kick because this photon goes isotropically. On the other hand, you can follow another path to go to the same final state, a neutral neon atom, that is this stimulated X-ray Raman scattering. So in this case, you have, the process is that you absorb two photons of slightly different energy at the same time. And one excites the electron and the other one de-excites the electron. And these two photons are traveling in the same direction. They're coming from here. So the neutral neon atom gets no kick at all. So it's not distributed. You just have the projection of this footprint on the detector, which you see very nicely here. So this was a very nice way of identifying these processes, which are normally completely hidden by, the more probable linear processes. And okay, so the question is, what can you do with this? Well, actually, this is really interesting because very soon we will be able to manipulate two photons at two different energies, and we will be able to choose what to excite, what atom and what level. And we will be able to follow, what's going on between two very well identified atoms and very well identified electronic states. And you can then start steering, chemical reactions and things like that. So there's a lot of potential in this kind of experiments. Okay, this is one experiment from MID, the instrument of Anders Madsen. So what you see here is coherent scattering, and the goal of the experiment was to use megahertz coherent scattering to identify the early stages of crystallization. Now, as you know, the way we understand crystallization, our classical description is a two-step process. You start from nucleation and then you have growth. So what does this mean? It means that at the beginning you have atoms that just sort of moving around, and then suddenly two of them can stick together or three of them stick together, but these clusters are too small to be stable. So they split up again. But when you start having, a little bit more, then they become stable clusters. And then they become, bigger and bigger, they become faceted, and then you have the growth of the crystal. Now, what is really interesting, which we still don't know, is the very early stages when you still have these unstable clusters. You want to know how order actually starts. And so in order to detect these unstable, really tiny few atom clusters, you need to have very short pulses, and you need to have a lot of statistics. So you need short femtosecond pulses and you need megahertz repetition rates. And then you put all this data together and you can use cross-correlation analysis to try to understand, the correlation in the scattering, coherently scattered intensity, for example, at two different angles. And then you can hope to get some information on the initial symmetries of your clusters. So this is very nice work, and it's not yet published, and we're looking forward to this paper. Okay, here I want to tell you a little bit about the first successful experiments using megahertz sequential X-ray photocorrelation spectroscopy. Now, this technique, again, is being developed on MID, and it's used to study fluctuation dynamics in systems that can be at equilibrium, but also out of equilibrium. So it works like this. You have a sample which has whatever kind of dynamics, so particles or whatever, they move around. And what you do is you send a train of pulses. So the first pulse, let's say, heats the sample, does something to it. And then the following pulses are able to probe what has happened and probe the dynamics. And each pulse creates a coherent scattering pattern. So you end up with a sequence of coherent scattering patterns. And from here, you can identify, through correlation, you can identify whether something has moved or not. Now, there are two things here that are important. First of all, in order for these techniques to work, you really have to be sure that the beam within the train, so all these pulses that come in within a train, have sufficient stability so that the changes that you see in the patterns are not due to the beam moving around. So that's really important. And that has been verified already at the beginnings, because this work was done actually before MID was open. It was done on another instrument at SPB, and they demonstrated that the stability of the beam within a train was sufficient to do these sort of experiments. The other thing that I want to point out is that since we have this megahertz repetition rate, the time distance between each snapshot is of the order of the microsecond, or let's say between 200 nanoseconds and 1 microsecond. And this time scale is a very important time scale for a lot of processes, especially in soft matter, in liquids and water, proteins. And so this is, finally something that the community was really looking forward to. So besides this first experiment, we've had 2 recent experiments. Again, these were virtual experiments carried out in September and October. We had 2 different groups working actually at the same time because they were using the same technique. One was looking at polymers, and they were looking at temperature-induced phase transitions in these polymers. So they had, these are little silica spheres coated with a polymer. At low temperature, the polymer is in a high volume state with all these sort of hairy features coming out. And then at high temperature, you know, this becomes much more compact and it forms sort of like a gel. And the other group was looking at non-equilibrium dynamics in proteins. And so they got a lot of data, and hopefully, yeah, we will be seeing some publications from these groups. Okay, so the last part of the talk I will devote to HED, which, as many of you know, is a little bit my area of research. At least I used to do research. I haven't done much in the past year. But I want to talk about what HED has done up to now and what it can do in the future. So here we have many different kinds of drivers to bring matter to extreme states. So we can compress samples using lasers, nanosecond lasers, or diamond anvil cells. So these drivers will bring matter into a state of high density, temperatures, you know, maybe up to a few electron volts. We also have drivers that allow to bring matter to very high temperature states. So we're talking about kilo electron volts of temperatures. So these are, you know, temperatures that you would have inside, you know, fusion reactors or in the center of stars. And here we have ultra high intensity lasers. So these are femtosecond lasers that deposit a lot of energy in these very short periods of time. Or we can use the X-ray beam itself to sort of isochorically heat a sample. And HED also has spent a lot of energy in developing, you know, new methods and testing new instrumentation. And I will show you some examples of this as well. So this is an image that schematically shows what the experimental hutch looks like. So you have here, the beam comes from the left. You have here 2 big interaction chambers, interaction chamber 1 and interaction chamber 2. And on the top of the hutch, you have these 2 very big labs where you have lasers. This is the high intensity laser, the relax laser, which provides femtosecond pulses, very high intensities. And this is the dipole laser, which is very similar to the one that we will have at ESRF. It's a 100 joule laser with nanosecond pulses. The only difference is that this laser will run at 10 hertz. Now, this is a picture of interaction chamber 1, and I'm showing it because I think that many of you know this guy. This is Valerio. He was at the ESRF for many years, and now he joined the HED team. And this is the inside of IC1, and you can see here Ulf Zastrau, who's the leading scientist of HED. So he's mounting here some supports for the big lasers. Okay, the first example that I want to show you is devoted to the development of diagnostics to measure, you know, thermodynamic properties of these extreme states of matter. So for us, pressure measurement is simpler than temperature measurement. So we're talking about extreme states of matter that only lasts, you know, less than a nanosecond or so. And the measurement of temperature is actually quite challenging. When the temperature is very high, you can use pyrometry, streaked optical pyrometry. But when the temperature is not that high, we still don't have very good methods. So what they do here is they use inelastic scattering to follow the energies of phonons. So they excite phonons, and then, you know, by just measuring the ratio between the Stokes and the anti-Stokes peak, they get an estimate of the temperature. And this is what they did here. This was just a diamond crystal, and they took the inelastic scattering in 3 different angles, so 3 different Q values, and they could estimate very nicely the temperature. You can do this also on liquids by looking at acoustic modes, or even on plasma by looking at ion acoustic modes. So this is another kind of experiments that are also pursued here in collaboration with University of Vienna and HZDR. these groups have been developing for many years these optics to polarize, to increase the polarization purity of X-rays. Now, the reason why this kind of stuff is done at XFEL is because we have already done similar, let's say, attempts at ESRF. And the idea is to exploit the very low vertical divergence of the beam. And at XFEL, we have a smaller angle, so smaller emittance and lower divergence, vertical divergence. And this should lead to higher purity. You know, this works simply by many reflections of the beam inside a very high quality polarizer crystal. So there was an experiment in 2019 where they demonstrated that they were able to reach through all these reflections 8 × 10⁻11 in polarization purity. However, what we can expect if we have, you know, better optics, but especially a more monochromatic beam, we can expect to reach 10⁻13 in polarization purity. I did not talk about seeding, but seeding is a way to manipulate the X-ray beam so that we have a smaller, let's say, a more monochromatic beam and much more stable beam. And we have successfully tested this at XFEL, and it will be available for users as soon as we can have users back. And you know, if you're interested, we can talk about this later. So this level of 10⁻13 is what we need to do some target experiments that are, let's say, requested by the community. So there's two types of experiments that people want to do with this very high purity beams, polarization beams. The first one is the measurement of magnetic fields in solid density plasma generated by Faraday rotation. I mean, yeah, so so what you have is you have a very high intensity laser, which creates a plasma, a solid density plasma. So you have these very highly energetic electrons that are launched. So they create hot electron currents, and then that generates a magnetic field. And, you know, the magnitude of these magnetic fields can reach 1,000 Tesla. And therefore, with such a strong magnetic field, you can deviate the polarization plane of the X-ray radiation of about 0.1 milliradians. So this is something that we should be able to do with 10⁻13 polarization purity. Another kind of experiment, which is also very challenging, is the detection of vacuum birefringence induced by a strong electromagnetic field, which is predicted by quantum electrodynamics. And here again, you have a high intensity laser, which actually is shot into vacuum. And so the idea here is actually to polarize vacuum so that when you have an X-ray beam crossing it, you rotate a little bit its polarization. Now, to do these experiments, you need a very high intensity laser, which we have and which we have commissioned. This is the relax laser. It's commissioned. It has not yet been used really by users because of Corona and everything had to be delayed. But we did do a quick test in August where we shot a tungsten wire with this laser, and we were able to measure the small angle scattering, which is shown here after this the laser shot. So this relax laser, we can say that is now, you know, available for user experiments, and there's a big community proposal that is waiting to do a first experiment on this. This is another nice experiment which was carried out during the Corona restriction time. As you can see here, everybody with masks. So this is the group of Dominic Kraus, who is now in Rostock, and maybe some of you can recognize him. He's here. Most of these other people are staff, HED staff members, very few users. So the goal of this experiment was to study the properties of low Z materials in the warm dense state, like carbon, silicon. And this is interesting not only because, you know, you can learn something about the interior of planets, but also because there's a lot of interest in looking at the formation and phase transitions in low Z alloys that have been created by shock, by impacts. impacts that happen either in nature but also in the lab. So people use these impacts to create new, very hard, low Z material alloys. So what they do here is they use the X-ray beam itself to heat the sample to this warm dense state. So they focus it, and the more they focus it, the more they heat the sample. And then they use back scattering or forward scattering to measure the temperature of the electrons and the ionization degree. So the ionization degree of the plasma is given by the amplitude here of this inelastic scattering, and the ionization and the temperature is given by the slope of this. And so they got very nice data, and here as well they are analyzing the data now. Now, the last example that I want to talk about are these attempts to couple diamond anvil cells to XFELs. So I remember very well this discussion, because we were all saying that we were never going to be able to do these experiments because the XFEL was just going to blow up the diamonds. And this is true. The XFEL can blow up the diamonds, but you can also find conditions where you can actually use diamond anvil cells and do very, very interesting science. So this was a big community proposal that took place in October 2019. There were 70 different people. It was very well prepared. So there was a lot of calculations to identify the temperature of the sample, of the diamonds, the thermal conductivity, the strength. And they were able to define the conditions that they wanted to test. And they did a lot of systematic work during this week by varying, the repetition rate, the intensity of the beam, and so on and so forth. And so here, for example, you can see that if you use a frequency of 4.4 megahertz, the sample heats, right? And it heats with this, seesaw thing shape. They looked at phase transitions, and they used bismuth at the beginning, which is more now, it has become a model system because it has a lot of interesting phases at relatively low pressures and temperatures. And they saw all these peaks and phase transitions. And then they did also a nice experiment. Well, they did actually many different experiments, but this was one of them, where they used the XFEL beam to induce the synthesis of a iron nitride compound at high pressure. So they put iron and nitrogen in a diamond anvil cell. They went to 5 GPa. So they had the solid nitrogen and iron, and they illuminated it with a train at a repetition rate of 2 megahertz. So every 440 nanoseconds, they had a pulse going through. And they were immediately able to see that temperatures went up to above 1,400 Kelvin because they saw the alpha gamma phase transition in iron. Then they kept on heating, and they saw the formation of this compound, an iron nitride compound. And they were able to identify the stoichiometry using the equation of state. And they also were able to identify after post-mortem analysis by doing a Fib analysis that the reaction was actually really, really homogeneous throughout the whole bulk of the sample. And so this shows that you can use these methods to really explore the time dependence of reactions and identify even new compounds that can arise at very high pressures and temperatures. They also developed emission spectroscopy coupled to diffraction, and they used it to look at a spin transition, a low spin, high spin transition in iron carbonates at 50 GPa in the diamond anvil cell. This experiment really was the commissioning of the ionization of the interaction chamber 1, which is typically not used for diamond anvil cell research, but they have this spectrometer, this emission spectrometer. And so there again, they played on the repetition rate of the XFEL to either maintain the sample temperature constant or to heat it. And this was a big collaboration. So these are the people that were actually involved in this in-house, this last example that I showed. This is the team on HED. And as you can see, I'm showing this because we have Christoph here, Christoph Saale, who was a very, very precious member of this team that really helped us to get this spectrometer and to interpret the data. And yeah, we really hope to maintain this very close collaboration with the ESRF. Okay, so I am now through. I tried to give you some, an overview of different kinds of scientific results in different instruments, different scientific areas. I think that we are starting to produce finally some science, but there's still many challenges ahead. And this is my personal view of what the big challenges are. So first of all, the most important challenge and the most difficult thing to solve is that we are still a very small community. We have groups that systematically get beam time, and it's always the same groups. To do experiments at the European XFEL, you have to be in a very big team. You have to have many people, all experts, because experiments are still really, really complicated. So we have to make a special effort in the coming years to make these experiments simpler, to really open the doors to smaller groups that can come and do their experiment. And this is really up to us to make this possible. And I think this is our main challenge, even for the sustainability of this facility. Another big challenge is the fact that we are catering both the soft X-ray community and the hard X-ray community. And the problem is that we have only one accelerator. And since at the moment we're working, in parallel, we always have 3 instruments that work at the same time. This is a big problem. This really leads to big compromises, because very often the parameters that are good for the hard X-ray instruments are not good for the soft X-ray instruments, and vice versa. So we always have a lot of issues in finding the right schedule, and it's always the result of a compromise. So we are now thinking about ways to mitigate this, perhaps even redesigning the SASI-3 undulator. We are trying to find ways so that we can do less compromises. Finally, we're still struggling with detectors. These are complicated detectors because we have this very specific beam structure. We have megahertz repetition rate, and then we have nothing for 90 milliseconds. And these are big detectors, and they produce huge amounts of data. We have still issues with the calibration, with having smooth data pipelines. At the moment, this is where we have our biggest instrumentation issues. Just to show you the amounts of data, of raw data that we accumulate. So these are some of the detectors we have. And if you look at this curve, it's a little bit scary, because if you think about it, up to now, we never had the 6 instruments operating with a megahertz detector, because actually we only have 3 instruments that have a megahertz detector at the moment. The 4th one is just starting, and the other 2 don't. And they never really worked together up to now. So when they really start working together, this curve is just going to go straight up as a wall. And this is really, really scary. So if you already look here, last year in 2020, where we barely worked because of Corona, we had very, very few experiments. We accumulated 10 petabytes of data. So this is something that, we're really, really focused on to try to see how we deal with this. Okay, this is my last slide. And I just want to say a few words as an outlook. In my opinion, this facility is still a young facility, even though, construction started in 2009. There's been big delays. First experiments took place in 2017. So, somehow, let's say we've already been working for a while, but, we still did not figure out how to do these experiments. And I think that it's going to take still a few years, and maybe we will be working in a completely different way. I think we still have not found the best way to exploit this facility. So I showed that coupling hard X-rays and megahertz repetition rate allows to do new things, to do new science. And this is really something which is specific to the European XFEL, because we had megahertz repetition rate before in the soft X-ray at FLASH, for example. We also had hard X-rays at LCLS, but we never had this combination. And so I think that this combination is particularly, promising for single particle imaging, and see how this develops in the coming years. Fluctuation dynamics, see how good we are if we have the sensitivity to do this kind of stuff. I think that looking at reactions at extreme pressure is very promising, maybe because this is my area, but I think that there's a lot that we can do there as well. And there's certainly many other things that I did not go into in this seminar. However, I still think that at the European XFEL, we have a lot of potential that still has to be exploited. For example, the instruments are not complete yet. We're not using the big lasers yet. We have split and delay lines, which are not yet commissioned. So these are going to be commissioned. We have many parts of the instruments that are not yet operational. Nonlinear phenomena, pushing this stuff into the hard X-ray regime using wave mixing techniques. This can open a lot of doors, and this is absolutely not done at XFEL yet. Actually, this is not done anywhere yet at hard X-ray. So this is something that we could eventually exploit. I think there's a lot of potential there as well. Coupling the X-rays to ultra-fast sources. This is not done systematically. So we have a lot of space here to improve using, for example, terahertz and seeing the response to terahertz excitation using X-rays. Special modes. The machine has been developing self-seeding, 2 colors. We can also shorten the pulses, have shorter pulses. Now they're of the order of tens of femtoseconds. We can go maybe down to the femtosecond. All this has been developed, but it has not yet been used. So, this is something that we are going to do, and we just need to get the beam time for this. And this is going to be done in the coming years. And finally, harder X-rays. This is a 3-kilometer thing, and we can go to 30 kV easily. We have demonstrated that the undulators lays at 30 kV, so we can use these X-rays, but we haven't done it yet. So you see, there's still a lot of potential that can be exploited, and it's going to take some time. So I'm through, and I thank you for your attention. I don't know how long it took, but yeah, I'm happy to have questions now.
Thank you very much, Sakura, for this really fascinating presentation. The work that you and your colleagues in XFEL are doing is really fascinating. Excuse me, I need to switch off this. Yes, so we are now ready for taking questions. So I remind to all participants that to ask your questions, you need to use the question and answer box that is somewhere at the bottom of your Zoom window. And I shall read the questions for Sakura until people send their questions. Maybe I start with one question. This concerns the magnetism Skermions you have shown. I didn't get what was the size of the samples and of the domains or Skermions that were visible, and I guess this was done by dichroism, circular dichroism. Is it correct?
No, actually, what they did was they had multi-layers, so I think the sample was quite big. But the size of the Skermions was a few. I think in their case was like a few tens of nanometers, and they saw the formation of these little particles by small angle scattering. They looked at the ring that forms. At the beginning, they have this very diffuse pattern, which shows that the spins are fluctuating. There is no order completely because it's high temperature. And then this cools down, and you start seeing the formation of a ring in the small angle scattering. And from that ring, they were able to identify, the average size of these Skermions to be a few tens of nanometers.
But where does the magnetic contrast come from?
Oh, no, that image is not done on the instrument. That image was coming from previous work.
Okay, it's another, okay.
Yeah, that was just to explain what a Skermion is.
Okay, then I get it.